Hello. Yeah. Am I audible now?
Cool. Okay. So guys, today's talk is all about like how Pratilipi with just like very less number of people that we are able to scale up to around 6 million users per month with just using AWS services that we leveraged. So, how many of you here have actually like know about microservices? Like, cool, good number of hands. So, so Martin Fowler once like famously coined the term for single responsibility principle that says like gather together things that change together for the same reason and like differentiate things that changed like for different reasons. So that is more kind of like in code level or in module level. So you take the same thing into a service level, what you get is something called as a microservice. It's an architectural style that structures an application as collection of small autonomous services that can live on its own. And collectively, like they'll talk to each other and solve a complex business problem in its own. So that is what like mostly is microservices. So now, so microservice is not something that is easy to get into. So if you know about the older structures of building applications, it's mostly like monolith where you have one code base, you build on it. So it's easy to work with. You're debugging in one place, so all these things. But the moment you like go into the microservice landscape, it is more kind of like very hard because you have like distributed systems talking to each other. How do you build it? How do you do the service discovery? How do you do the debugging? So everything becomes hard. Now if that is the case, why should you go for microservices? So one thing is like independent development. So microservices are like small services that even a very small team can handle. Maybe like 2-3 people could code on it. So it's very easy to develop. The other one is independent deployment. So if you have a monolith, once it grows like really big, you want to change a very small part of your code, you have to deploy your entire application as one. So if it is a microservice, you know like you want to change a small service, you do it, you deploy it. So you know the blast radius. So it's not too risky on doing that. So the next one is fault isolation. So in case of a monolith services, it's either mostly like binary. You either have the service or you don't have the service. So if in case of a microservice, you can degrade your systems, gracefully. Say if in case of Pratilipi, you can read and write. Now, there could be a separate service for review. Now, even if the review service go down, you still could use the Pratilipi as it meant to. So it degrades gracefully. So that is one of the advantages. The other one is mixed technology stack. So if you have a large code base that is like handled by one, there will always be like, you'll be adhering to some kind of technology stack that is there. So you are retrofitting your solutions to the technology stack you already have. But ideally, it should be the other way. When you have a problem, there could be some right set of things that you could use to solve that problem. So microservices help you in that way. You could choose like any tech stack that you want. Whether it could be like language, database, or build structures, whatever it is, frameworks, whatever it is. And then comes granular scaling. So most part of a code, there could be like some hotspots that like hits more than the other parts. So if it is a monolith service, it's like you either scale it as one, like you will have multiple things of the same monolith running in multiple places, which might not be efficient. In case of microservices, you scale up those things. Say if it is recommendation is the one that is like really high, that needs high CPU, you scale just the recommendation service when needed. So it's like it helps in granular scaling also. Okay, so this is a scale that we handle. We handle around 800 million API calls every day, and at our peak time, we handle around 300,000 requests per second. So how do we do that? So the first thing that helps us do is containers. So I'm not sure how many of us have heard about containers or Docker. Cool. So containers is the one that actually made microservices possible. So even though microservice was a concept, this was the one that made us do it. So it's an abstraction of the app layer. It's more kind of like if you have an executable when you build something for a programming language, this is another way of building an executable that can run on any system that has a container applicable to it. So we are using Docker. So the thing with Docker is, even pre-Docker, you had something called as virtual machines. So if you have multiple processes running on the same machine, that has to be isolated. So you have a machine, you have a hypervisor. On top of that, you run multiple operating systems on top of it. They are called virtual machines. So there the issue is, the virtual machine itself will run into GBs of size. The operating system itself will be GBs of size. Then your app will be some MB. So actually, you are wasting most of your resources on running operating systems on top of operating systems than for your actual apps. So in case of containers, what happens is, they share the underlying operating system and the kernel. So they have the same kernel. So essentially an app is like very small things, but still you get the same level of isolation that you get with the virtual machine. So this is what helped the most in having a microservice architecture like to scale up. So there is essentially no wastage of the actual physical resources, and they still have like very isolated processes. Now, so this is one of the services that we use, that is Elastic Container Registry. Now once you build a container, so what you get is a container image. So that image you have to store somewhere so that later you can like pull it and run it somewhere. So AWS provides one called as Elastic Container Registry. So what we do is we code, we build it, we get what we essentially get is a container image, you upload it to container registry. So it's stored there, it's easy to manage, it's like very secure. So only like with certain roles you can access these images. So all the security thing will be handled by AWS itself. So this is one of the part of the puzzles, Elastic Container Registry. So this is how it works. You write code, so there's easier running on there. It gets pushed to it. So all the security is handled by it. So whenever you want to run yours, you just pull it from there and run in whatever place you want. Now the second part of the puzzle is Elastic Container Service. Now once you have the image, you need some place to run it, actual physical machines, right? So that is where Elastic Container Service comes into play. So this is also maintained by AWS where it gives you a cluster of machines to run. So essentially it's like you might have like 10 or 20 physical machines running in your background where you could run your containers. So suppose you say for recommendation service is an image in is a container, and that needs maybe like 512 MB of RAM to run and 256 CPU units. So there need to be actual machines to run it, and ECS is the one that handles the clusters for you. It's a highly scalable, high performing one. It supports Docker containers. So all these machines will be having Docker installed in them. So how it happens is you have the Elastic Container Service, you have the container registry that we talked about. So we build, we push it to container registry. Now when you want to run it, you define what you want to run. So you say, okay, I want to run maybe content service and take this image from Elastic Container Registry and run it somewhere. So Elastic Container Service will take it and run it in whatever place you need. So that is the second service that AWS provides. Now the third one is load balancer. So now you have built an image from your code, you have it running somewhere. Now if somebody gives a request, it has to reach your service, right? So that is the third part of the puzzle that will be solved by the load balancer. So it actually like gets the incoming service, incoming request. Based on some rules, it will route it to whatever things you want, whether it is EC2 machines, lambdas, IP, specific IP address, whatever it is, even to containers. So this is the third part of the puzzle. This is how we do it, just like a sample from a prod itself. So if you see here, you are mentioning a rule. You are saying if the request comes to port 80 and it comes to /auth, go to your auth service. Comes to /user, goes to your prod user. So here you mentioned the rules like, okay, when this happens, goes to this place. So now you have the three parts solved. Like you have the image stored somewhere, the image is being run somewhere, and now you are able to route the request to that place where the container is running. Now, so these are like three things. Now the fourth thing is, now you have your services running. Now you are getting like, say, one of your service can handle 100 requests. Now at the peak time, say 500 requests comes in. So what do? So now you might have to run like maybe 5 services. So that is also handled by ECS. So how do you mention it is, you mention it like rules. So every rule, ECS makes sure this is getting met. So for example, we are saying if a single service can handle only 170 requests. So if 200 requests comes in, Elastic Container Service will spawn one more service. So essentially you have 2 services and goes down 170. Another route could be like CPU utilization 80. So if the CPU utilization goes say to 90, it might spawn one more machine to make it back to like below 80. Like whatever the rules there is. So ECS will make sure based on these task rules that it has sufficient number of services to run whatever request that comes in. So it scales up and scales down as necessary. Now when you said like, okay, you're getting more requests, you need more services to be spawned. Now when you have more services, there need to be like places to run that services, right? So if you have only 1 GB of RAM and like 2 core machine, and if you want to run 6 services, you are not able to run it because you don't have physical spaces to run services. So that is where you do the cluster scaling. So there also the exact same thing as services. You say, okay, target value is 70 for CPU and 85 for memory. So then what happens is, if you have 2 machines in the cluster, and if say more requests are coming, so you need to install like say 5 more services to spawn, and then suddenly the CPU spikes up. So if it goes above 70, what ECS will do is it will maybe attend 1 more machine and add to the cluster. So that way it like scales up. And once the request goes down, so all these usages will go down, and then it will like remove the machine from the cluster. So it scales down in that way. So if you see here, this is what happens. So you have the CPU usage at 70% because that is what we mentioned. We asked them to always keep it like that. So if you see the drop there, what could have happened is the number of requests reduced. So the cluster's usage came down, and once it came down, Elastic Container Service could have moved like out some machines from its cluster. So if it had 10, it would have made it 8. So that again it became like 70. So ECS will make sure this is maintained by itself. This is like the entire flow, what happens when a request comes till it gets served in a server. So currently we have like web and mobile client. It comes to our external load balancer, the load balancer that we talked about. So this is the internet facing one. So you have the external load balancer, it comes there, it has 3 rules, saying if it's slashed with /API, go to our API gateway. If /GraphQL, go to our GraphQL gateway, else go to the web gateway. And then in API gateway, if it comes with an access token and you're trying to access an API, so this is where the check happens, like you resolve the token using auth, you get the user details, what are his roles and all, and then you figure out whether he is like able to do that operation. If so, give it to the internal load balancer. So this is another load balancer that is not internet facing, and from there it says, okay, /content goes to content, /author go to author, web goes to web. And parallelly, you will be doing the development, maybe in GitHub. You build it, upload to ECR, ECS pulls the latest image, and you get it deployed to production. So you have your latest code always in production, and now say when the number of requests increases, ECS will make sure it adds more number of tasks. Say author will be running 5 tasks, content will be running 3 tasks, and once it runs out of space to run it, you have the cluster scaling rules to increase the cluster so that more tasks are run. And once the number of requests reduces, it reduces the cluster. So that way it makes sure your system is always at the optimal space in which it can handle all your requests. So some of the things like we learned, so one was like hypothesis, with this development what we learned was, one was hypothesis driven development. So whenever you go for something, it's always better to test it out with some set of users so that you will actually know whether it is such a cool feature. Because if you talk within your company, it might be like 10 people, you might think it's cool. So once you like try to test it out with a larger set, it might not be that cool. So rather than wasting your time in like building things that is not worth it, it's always better to first test it out with a set of your users and then build it like in the right way. And once you're pretty sure like this is what you want to build, then always build for your 10x. Like if you have a traffic, always build for like 10 times your traffic. Not like a proper number, but yeah, always aim for 10 times your traffic that you have. The other one is the system can be more asynchronous than you think. So whenever a request comes, you do so many operations in between and finally you send the response back, right? So that is the response time. But if you look closely, most of those flows might not need to do most of the things like in the flow itself. So maybe you could push something to Kafka as an event-based one, or maybe to a job queue. So there could be so many things that are asynchronous in your flow that if you could find out and like send it to somewhere else, that itself increases the performance of your system. The other one is leverage caching. So caching also plays an important role in your system's entire performance. So wherever it is, whether it is at the CDN level, or you have an Nginx on top of your server, or it is like you're using a Redis and reading from there. So whatever it is, caching also plays a very good role in the actual performance of your system. And monitoring and logging. So they should be like really good, like your user should not be coming back to you saying like your system is not working. You should always be on top of it, and you should know when your system breaks. So monitoring and logging should always be like built into the system itself. And finally, hire the best and trust them. So if you hire someone the best, you can always trust them to build it the right way. So that's it. So these are some of the tech stack that we use. So programming languages, we mostly code in Golang for our services, and for some we use Node.js. Java we use for some streaming services, and then you also use Python. And the front-end framework that we use is Vue.js. Docker is all built, and Jenkins is the one that we use to build. Other than that, we also use Firebase DB. And for the GraphQL, we use Apollo, that is given by Apollo for Apollo GraphQL. And databases, we mostly use MongoDB and a combination of Mongo and MySQL. That pretty much sums up what we do. So if you have any more questions, feel free to ask. Can someone give the mic?
Hello. My question to you is, can you go in a bit detail about how the different services in your market, this microservice architecture interact? Like what protocols do you use?
You want to talk about this?
Yeah.
So mostly they talk to each other in HTTP standards.
So normal HTTP, like 1.1.
From the external, it could come with 2.0 also, but internally they will convert it to 1.1 to have it with the internal services.
Yeah.
They have tried for gRPC also, but that is way too much with the AWS infrastructure, which is GCP, it's a bit more easier, but in AWS you have to have a lot more things built in to have gRPC built into your service. So we mostly use the load balancers, and I think from externally they will support HTTP 2.0, but internally they will convert back into HTTP 1.1, and then while returning back, they'll still convert it back.
And what about the internal caching between the services? Do you use any kind of caching between the services?
So like I mentioned, so every service is a self-sustaining thing. So if you want to cache, the web is calling something and web want to cache it, web can decide where you want to cache. If you want to cache it in Redis, you do it. Say if web is a server running and it has an Nginx on top of here, maybe from the Nginx level itself, we can give back the request. Or whether if you want to do it from the CDN, even before reaching the LB, external LB, maybe we can serve it from the CDN itself. So caching depends on, every service can decide what to cache, when to cache, and how to cache.
And regarding your, you chose MongoDB. Is there some specific reason you chose MongoDB in comparison to some other database? I want to know.
One thing was it was getting a lot of traction and it was scaling well for us. It's not like other NoSQL databases are bad, but MongoDB was working well for us. So that is also one of the learnings I would say, always go with your convenience. There could be other cool techs also out there. Whatever you're good with, if it fits to your problem solution, then go for it.
Hello? Over here, this to your left. Yeah. Hello? So, okay, great talk. Right. So, one thing that I wanted to ask is, how do you do the cost-benefit analysis of going up for choosing a particular service? For example, rather than the ECS, you could have gone for a COPS cluster or something similar, right?
So what we do, even in ECS cluster, I just wanted to leave that part out, not to make it too tech talk. So even with ECS cluster, what we do is, when I told you you want to add more machines to it, so what we do is, AWS gives you 3 types of system. One is a reserved instance, so where you buy it for a year or 2 years, you commit for it and you buy it. The second one is called the on-demand, where you buy it for an hour or 1 day or something. The third cheapest one is called as the spot instances, where you bid for it. So whoever is the highest bidder, get the machine. The only issue there is they'll take it back anytime they want when the bid goes high. So what we do here is, we have something called as spot fleet request. So that we attach to this ECS cluster saying, okay, I want these 2 types of machine, I'll bid for this price. So whenever the ECS cluster want to scale, it bids for it, get these spot instances, attach it to the cluster and runs it. Whenever it goes out, we again bid it. So that way, our entire cluster in production, I think it costs around $3,000 just for running the services. So that is how cheap it is. For that, we are using spot instances.
Okay, so another thing that I wanted to pick your brain on. So AWS Lambdas are notorious for the cold starts, right? Mm-hmm. So how do you manage that? If you use Lambdas.
So serverless architecture is entirely different. You want a different kind of thought. this one was working better for us, so we didn't want to like get into the cool stuff just for the sake of it.
Okay, cool. Thanks.
Hello. Hey. Yeah. Hi. Congratulations on scaling your product so efficiently. So I just wanted to ask you mentioned your microservices talk to each other via normal HTTP calls, right? So how do you deal with the communication problem, like one microservice talks to another?
You're talking more in terms of like chatty services.
No. So basically, like if there is a failure at one microservice, how do you implement retry mechanisms for all of that, right? Do you use probably a queuing system wherein some microservice consumes? How do you implement like retries?
So the thing is, at the service level, one thing even before that is we try to make sure our services are as less chatty as possible so that they don't need to talk to each other. So if you build a microservices in the right way, mostly they'll be doing CRUD operations.
Okay.
So they might not need to do it each other. And then, so even before this layer, we actually have another layer built that is called as the backend for front-end architecture. So even if you want to aggregate from multiple microservices, you use that service. So most of the UIs will be using that services so that your actual web services need not like talk to each other at the same level. So that reduces the chattiness one. The other one is most of the things we made it like an event pipeline so that they don't need to directly talk to them synchronously so that in that pipeline you can do the retry. Now the third one is the question that you were asking is mostly kind of like how you want to gracefully like degrade your performance. Say if this is not working, whether you want to send back a 500 or not.
Yes.
And then it could be like maybe circuit breaker patterns that you could do so that you don't even, like after 5 times, maybe you will not even try to hit it for next 5 times, and then you have it like half open, then you try it once.
Yeah,
so it's
where
like,
where does that logic reside? Does that decide at the calling microservice level or does that decide at the load balancer level?
it lies in the services itself. So it can't lie in the load balancer. Load balancer is mostly kind of like very stupid that can only read the actual URLs and probably the headers and do rules and routing, nothing else. At least the elastic load balancer that gives you. But if you go for like something like a mesh architecture, say with a sidecar proxy, and you have an entire mesh that says Istio or Envoy or something like that, then they will have that retry mechanisms and all built into them.
Okay.
But for a normal elastic load balancer like this, it is very dumb.
Okay. And one last question: how do you deal with like a dependency hell sort of a system wherein another microservice needs to be deployed for, let's say your auth microservice needs to be deployed first for probably your other user microservice to go up? So how do you take care of a dependency hell sort of a situation where even though they can be deployed independently, but one needs to go before the other, probably for the...
We do something called as canary deployment. So what we do is we have 2 clusters. So even this cluster, think of it as one cluster here and one cluster here. Okay? So this cluster is having auto scaling enabled for it. But this cluster will be having a fixed number of tasks running. And the load balancer will be giving to both. Okay? So now say for content, you have 9 services running here and 1 service running there. So when we want to deploy, what we do is we first deploy into that cluster. So essentially 10% of your traffic goes to there. So we make sure it is working fine, then we give it to this cluster. So once this works fine, then you can maybe update the second one. Say if it is web and content, so once we make sure web is in prod and working fine for 100% of users, you can update the content task and say, okay, now go to ECR and take the version 2 of me because web is now stable. Same thing happens. You go to the canary cluster, deploy it there for 10%, things work fine, you go here.
Makes sense. Thank you.
Any more questions? All good. Okay. Thank you guys. You have been a great audience.